So the first question I kind of want to ask you guys is, how'd the test go?
I thought I did better than I actually did.
That's, yeah, okay.
Me too.
I thought it went well.
Okay. Was the sort of multiple choice question style better than the keep doing the exactly like the homework style, or was that kind of what threw people?
I really like the multiple choice.
Okay.
I don't know. I just ran out of time a little bit at the end. So
Okay. Yeah, some of those questions can take a little bit of a time. Yeah. I haven't looked at scores yet, and I need to go back and do some of the scratch work grading stuff. So I'll do that, and I'll get scores updated this week. But it's good that it sounds like it felt better, even though maybe it was tougher than you anticipated, maybe. So chapter 5, we're going to finally get into some integration stuff, and we've got to build that up a little bit. So I'm going to start drawing some pictures and talking about integration here. So the idea of integration is that there's two ways to think about it. It's to think about it as anti-differentiation, and we've already talked about that a little bit. And so we're going to go with the geometric way to think about things. So to demonstrate that, let's draw some pictures. And let's pretend that we have a velocity function here. Let's call this v of t. And here's t. And if I know how fast I'm going at any given time, well, the antiderivative of the velocity is the position, right? So let's see if we can figure out what the position is based on just the velocity function. And so this is at 1, 2, we'll say that it ends at 5. So we want to know what the position function, find an approximation for s of t, position function. Well, over the first second, it looks like we're going about 1 unit per second. Let's say that this is in units per second. And this is in seconds. Then if I'm going approximately 1 meter per second for 1 second, after 1 second, I've gone about 1 meter, right? I've gone the area of this green box. Over the next second, there's some value in here where on average, I'm maybe going about 1.5 meters per second, right? So the distance that I go in this next second, the velocity here is about 1 3/4. This is about 1 1/4. So somewhere in the middle at about 1.5, right, meters per second is how fast I'm going on average throughout this interval. And so how far I've gone would be how fast I've gone, which is how tall the rectangle is, by how long I've been doing that, which is how wide the rectangle is. We do that for the next box too. And then somewhere here in the middle is about the average speed that we're going, which looks like it's about 2. So in this rectangle, I'm going about 2 meters per second for a second. So I've got another 2 meters, which is the area of this rectangle, meters per second by seconds. Then there's this guy. Sorry, there was somebody yelling outside my window really loud. I don't know if you heard it, but he was angry. So that height is about 3.5. So I go about 3.5 meters for the next second. And then this last rectangle is about 5 meters tall. So I go about 5 meters for that last second. So S of t is going to be approximately given by this table here, where t at 0 seconds, well, at 0 seconds, I haven't gone anywhere. At 1 second, I've gone the area of this box, which was 1. At 2 seconds, I've gone the area of the first 2 boxes, which is 1 plus, what do we say that was, 1.5. After 3 seconds, we've gone the area of the first 3 boxes, plus 2. So that's 9/2. After 4 seconds, how far have we gone? We've gone 9.5 plus another 3.5, which is 7/2. So that's 8. And then finally, after 5 seconds, we've gone that 8 plus another 5, 13. So we've kind of got our position function based on the area of these rectangles. The idea then is that this was just an approximation of the area under the curve by these rectangles. Because if I draw smaller boxes vertically and I approximate those areas, I get better approximations to the curve here, better approximations to the area under the curve, because I'm not having as much freedom in how much error I get, in the sense that, like, the error was all this stuff that was above the curve that I was missing extra. And then there's also this stuff below the curve that I didn't actually count. That took everything in. Like, I didn't count this bit here, right? Didn't count that bit there. Well, I guess with the green one I did. That one I didn't count the outside stuff. That one I didn't count the under this curve stuff, right? There was some under the curve stuff that didn't get counted in here. There was some over this curve stuff that got counted, so that was extra. But if I refine how many vertical rectangles that I draw, those rectangles are going to be closer in height to the actual curve there. And so in sort of a limit, as I draw more and more rectangles, the area of these boxes gets closer and closer to the area under the curve. And so this section's all about trying to figure out, how do we approximate areas under the curve? And this method here that we did to start with is kind of the first idea of that. So let me formalize some of that in some algebraic language here a little bit more. So we're going to have a function f of x, and it's going to be on an interval from a to b. And we're going to say that the integral from a to b of f of x dx, this is just notation for the area under the curve from x equals a to x equals b. Okay. And it's not a coincidence that this is the same as the anti-differentiation symbol, right? The integral and the anti-differentiation symbol are the same thing. This one's called a definite integral because it goes from two specific endpoints. If I don't have endpoints on there, it's called the indefinite integral. But there's a relation between the two, which is the fundamental theorem of calculus. Okay, so let's go back up to this problem again a little bit. Right, we started with the velocity function. We found the area under the curve, and we got the position function, right? Usually, if you take a position function and you take a derivative, you get the velocity function. Right now, I'm starting with a velocity function. I'm finding an area, and I'm getting a position function. So that should be your first idea that these things are inverses of each other in the sense that integration, finding the area under the curve, is the inverse of differentiation, finding the slope of the graph. Okay. Now, these rectangles that we draw, in this class, we're going to make it easy and make sure that all the widths are about the same. So I'm just going to take b minus a. That's how far along the x-axis we have to go. And if I want to break that up into n rectangles, I'm going to call that delta x for this situation. So if I want, I don't know how many this is going to get me for, 5. If I want 7 rectangles, right, I'm going to take b minus a over 7 is delta x. That's how far each one of these is apart. There's a delta x here, delta x there, delta x here, delta x here, delta x here. That's the width of each of my rectangles. If they weren't uniform, and I don't have to have uniform width rectangles, maybe I have sort of some narrow ones and some fatter ones. What delta x is, it's still just the change in x. So I'm going to label the endpoints of the rectangles like this is x0 is that first x1, x2, x3, x4, x5, x6, and x7 are really close together there. x8 and x9. I have 9 rectangles from x0 to x9. And what delta x is, it's the width here. So this would be delta x1 for the width of the first rectangle. This is delta x2 is this width, and so on. So delta xi is equal to xi plus 1. Oops. Minus xi. And that's just the width of the ith rectangle. And I haven't actually given you a rectangle yet because I haven't given you a flat top on these things yet. So somehow we're going to have to figure out how to put tops on these rectangles. Maybe it's I find the biggest point in this little interval here, which would be right there, and I extend the rectangle that way. Or maybe I'm in here and I find the smallest point on the interval, which would be right there, and I extend the rectangle from there. So like on this guy, the smallest point is kind of in the middle here. And so my rectangle might be like that. I could just decide to take all of the right-hand endpoints and make all of my rectangles from the right-hand endpoints. And then some of them would overestimate and some of them would underestimate. Oops, that one goes all the way over there. That one's a really big overestimation. I could take the left-hand endpoints and pick those guys to be where I make my rectangles. There's lots of ways to pick the rectangles, and For the functions that we look at in this class, it doesn't matter which endpoint you look at or which point inside the rectangle you look at. You could look at a minimum point, you could look at a maximum point. For continuous functions, we're good with picking any of those points. The book has a few nice ways to do it, which is the left-hand rule or the right-hand rule. There's the maximum rule, the minimum rule. Those are a little harder to actually compute because if I was trying to find the maximum point in this interval, I would have to do some calculus, differentiation calculus, to figure out where's the derivative 0 and then find that and then figure out what the maximum value is. But if I'm just asked for the left-hand point or something, I could just take my function f of x, and this point here is f of x of 4, right? And so I could figure out that at x4, f of x4 is where my height is, and I can get my rectangle that way. Okay. So this is just a lot of notation and a lot of sort of just algebraic geometry, drawing pictures and labeling things right now. Do we have questions on any of these labels and pictures and that type of stuff? Because the notation's new. Okay. So let's do a left-hand estimate for the area under f of x equals, let's say, just x squared plus 1 from x equals 2 to 4 with, let's go with 4 rectangles. We'll say equal width rectangles. Okay, so let's draw this picture a little bit. So I have x squared plus 1. So I've got a parabola here like this. I'm going to go from 2, there's 1, there's 2, 3. Let's stretch that out a little bit. One, 2. No, why does it stretch it out? That just got things narrower. Stretch. Okay, so I want to find the area from here to here. And I want to do it by using the left-hand estimate. That means I'm going to use left-hand end points on my rectangles to decide how tall the rectangles actually are. And I want 4 equal width rectangles. So the first thing I should figure out what delta x is. Delta x is going to be 4 minus 2 over 4, because I want 4 rectangles. So let me label this. This is the right-hand endpoint. This is the left endpoint. And this is the number of rectangles. And so delta x in this case is 1/2. So each of my rectangles should be half a width, half a unit wide. So I'll have one at 2.5. I'll have one at 3.5. So I can put my verticals for my rectangles in. Okay, so each of my rectangles has one of these verticals in here. And then I should have a vertical start. So those are the uprights on my rectangles. And then the left-hand estimate says I'm going to take the left-hand endpoint of each of the rectangles, figure out where it crosses the function, and then that's going to be where I draw my horizontal bit for my rectangle. So here's the left-hand endpoint where it crosses the function. Come over, that's the top of my rectangle. Where the left-hand side of the rectangle hits the function, come over, that's my rectangle. Left-hand side of the function hits the function. That's where we have our rectangle. So I'm underestimating the area under the curve, because the area under the curve that I'm not getting is that bit. I'm not getting that bit. I'm not getting that bit. I'm not getting that bit. But this is an estimate for the area under the curve. It's just an underestimate for the area. So let's add this stuff up. So we're going to add up a width of 1/2, which is delta x. And then I have the left-hand endpoint, that's f of 2. That's the height of this first rectangle, is delta x times f of 2. Plus, I'm going to have delta x times f of 3 would be the height of the second rectangle. Plus delta x times f of 4 is the height of the third rectangle. All the widths are delta x. And then the last rectangle would be delta x wide times f of, my left-hand endpoint for the next rectangle is at 2.5, right? So I want f of 2.5. Then I get to take the left-hand endpoint's 3. And then I get to take the left-hand endpoint's 3.5. I was getting a little carried away. I wasn't doing just integer stuff. Okay, so the left-hand endpoint is 2, that goes in there. The left-hand endpoint is 2.5, that goes in there. Left-hand endpoint is 3, that goes in there. Left-hand endpoint is 3.5, that goes in there. 4 doesn't actually, it's not the left-hand endpoint of any rectangle because it's on the right-hand side of the interval. It's never going to be the left-hand endpoint of our rectangles. So we add up these 4 values. Those are the 4 areas of the green rectangles. And that's our left-handed estimate for the area under the curve. So let's factor out the delta x. Delta x is part of each of these. So this is equal to delta x times f of 2 plus f of 3.5 plus f of 3, that's 2.5, 3, and then f of 3.5. Okay, so that's going to be 1/2 times f of 2 is 2 squared plus 1 is 5. 2.5 squared is 6.25 plus 1, so that's 7.25. 3 squared is 9 plus 1 is 10. And then 3.5 squared is, I think, 11.25 plus 1 is 12.25. Okay. So we add this up, I get 15, I get 19.5. 19.5 plus 15 is 35.5. I take that in half, that's going to be 17 3/4. That's going to be our approximate area under the curve, x squared plus 1 from 2 to 4. Okay, do we have questions on that?
How come you don't take the 4?
So the 4 is the right-hand side of this green rectangle,
Mm-hmm.
but we want the left-handed estimate.
Oh,
So this is
okay.
rectangle 1. This is rectangle 1. Rectangle 1 has this thing as its area, right?
Yeah.
2 is this one. 3 is this one. Fourth rectangle is this one.
Mm-hmm.
The area of rectangle 4 is this guy. And so I'm not using the 4 as the height of that rectangle. If I was doing a right-hand endpoint, then I would use f of 4 to get the height of the rectangle. But I'm using the left hand, so we don't have that 4 there. Does that make sense?
Yeah.
Any other questions on here?
How did you get the values 5, 7.25, 10, and 12.25?
So f of x is equal to x squared plus 1, right? So f of 2 squared plus 1, f of 2.5, 2.5 squared plus 1. This is 5. This is 7 1/4, and so on.
All right, I see that.
Other questions on this? Okay, let's do one with the right-hand rule, right-hand estimation. Gonna be similar. Let's do a right-hand estimation for the area under y equals, do x squared here, from x equals -1 to 3 with 4 rectangles again. So first thing, I'm going to draw my picture. I'm going to start at -1, 0, 1, 2, 3. So my verticals are there. This time I want to use the right-hand estimation. So I'm going to use the right-hand endpoints of these rectangles to figure out how tall the rectangles are going to be. So on the last one, I started at the left, went up, and then came over, went up and came over. I'm going to start on the right this time because 3 is the right-hand side of the last rectangle that I draw. So I'm going to come up to where the graph crosses this vertical and move over. And that's going to be an overestimating rectangle. Then the next right-hand side of a rectangle is here at 2. I'm going to come over. That overestimates this one. This guy comes over, down. This one at 0, there's not actually really a rectangle there because the vertical bit crosses the function right at 0. So the right-hand rule says that this rectangle is 0 height. That's fine. So I have these 4 rectangles, well, these 3 rectangles and this non-rectangle to add up their areas. So let's find delta x specifically. Again, I take 3 minus 1. That's the right-hand side minus the left-hand side over the number of rectangles that I want, which is 4. So delta x is equal to 1, which is how we got our rectangles here. Probably should have done that first and then put in those rectangles, but with the integers being as they were and the delta x being 1, that wasn't too bad. Okay, and then the height of this rectangle is going to be f of 3. The height of this one is f of 2. The height of this one is f of 1. The height of this one is f of 0. So what I'm going to do is I'm going to take delta x. They're all the same width, so I'm going to factor that out right away. Then the height of the first rectangle is f of 0. The height of the second rectangle is f of 1. The height of the third rectangle is f of 2. The height of the last rectangle is f of 3. So I'm going to take delta x, which is 1 times 0 squared plus 1 squared plus 2 squared plus 3 squared. And it's going to be 9 plus 4 plus 1 is 14. So the right-hand estimate for this area is 14. There's part of it's overestimating, right? This part's overestimating, this part's overestimating, this part's overestimating. But this very first rectangle is underestimated, right? So part of it's overestimating, part of it's underestimating. It depends on if the function's increasing or decreasing or what on the interval that contains that rectangle. But this is an estimate for the area under the curve. It's not just an overestimate though, because I've got this underestimated bit. Okay. Are there questions on that calculation? Okay, let's look at some of the homework from the section. This one, it just says evaluate the function p at a point. That one's just part of stuff. This is more just evaluate at points, sort of review question. Here's one where we're supposed to use a lower sum with two rectangles of equal width, a lower sum with four rectangles, an upper sum, an upper sum. Okay, so these aren't left and right, these are lower and upper, which means that I'm going to be looking for the maximums and the minimums. But because of how this thing's set up, on this interval from 0 to 4, the x squared function, that's going to be a left or a right because this thing is monotonically increasing from 0 to 4. So let's draw a picture. There's 0, there's 4. Tells me how many rectangles in the I bit. Okay, so I've got 4x squared. So if I want just two rectangles, I'm going to take 4 minus, 0, because I'm going from 0 to 4. I'm going to divide it by 2. So 2 would be delta x for two rectangles. All right. And so I can put in my rectangles at having uprights at 0, 2, and 4. We want a lower sum, so that means that I want an underestimation. I'm going to take the smallest point on the curve, and that's going to be the height of my rectangle. So that one is going to be a non-rectangle again. The first rectangle is just going to be a rectangle of height 0. Then a lower sum with two rectangles. So on this interval, where's the lowest point? It's right here. So that's going to be my estimate for the area there. So for I get two rectangles, both have delta x equal to 2. So I'm going to take 2 for the width, and then I factored out the height. So that's the width of each of the rectangles. The height of the first one is 0. The height of the second one is 2, as f of 2. F of 2, 2 times 0 plus, the f is 4x squared, so 4 times 2 squared. That's going to be 2 times 16, 32. So my lower estimate for the area on this one is going to be 32. Okay. If I want to do a lower estimate using 4 rectangles, let's put in 2 more rectangles. Let's put in 2 more rectangles. They'll start at 3 and at 1. My lower estimate still uses the lowest point on the interval, so that's going to be a non-rectangle there. At 1, I'm going to have a rectangle at f of 1. This one's still the same height, but it's only half as wide. And then this one's at 3, and that's going to have the height 3 there. So I want the blue area this time. And my widths are only going to be 1. Delta x is going to be 1. I'm going to have 1 times my lower estimate is 0 plus 4x squared at 1 is 4. Uh, 3 is 9 times 4 is 36. So I'm going to have f of 0, 0, 4 plus 16 plus 36. That's going to be my areas under those 4 rectangles. So my left-hand estimate is 1 times 4 plus 16 is 20 plus 36 is 56. So my lower estimate using 4 rectangles is 56. Okay. Same thing with upper rectangles. So 2 upper rectangles. I'll have rectangle there, rectangle there, rectangle there. So I'm going to come out to 4, and my upper point on this interval here is over here at f of 4. My upper point for the first rectangle is here at f of 2. So delta x is 2 because I only have 2 rectangles. And then I have f of 2 plus f of 4 are the heights of those 2 rectangles. So that's going to be 2 times f of 2 is 16 plus 4 times 4 squared is 64. That's f of 4. So it's going to be 2 times 80 is 160. If I use 4 rectangles, purple. The upper sum here, the upper sum here, the upper endpoint here, the upper endpoint there. Those are the 4 rectangles I would get from the upper sum. So I have 1 is my delta x. And the first rectangle has height f of 1. The second rectangle has height f of 2. The third one f of 3. And the last one f of 4. And so the right-hand upper sum for 4 rectangles on this is 1 times 1 was 4 plus f of 2 was 16 plus f of 3 was 36 plus f of 4 was 64. So I add that up, I get 80 there and 40 there, so 120. So this is 120. Okay. Where do you have questions on that one?
Would there ever be an equation where like the lower sum or the upper sum isn't one of the left or right points?
There are. I really don't think the book would give them to you though.
Okay.
So like in this picture, right, we had the the lowest part of the curve was right there, which isn't on one of the endpoints. Like in this picture, the uppermost part of the curve is right there, which isn't on the endpoints. The lower part's there. So yeah, if your maxes or mins, your local maxes or mins happen inside the interval, then your upper rectangles and your lower rectangles aren't going to have endpoints as your values, but the book's going to give you monotonic functions so that you get endpoints. But yeah, be aware that it could happen. But other questions on this? Oh, let me point one more thing out here. Okay, the lower estimate is going to be an underestimate, but as I add more rectangles, it's going to be less underestimating, right? Here it was 32, which was way too low. I added 2 more rectangles and I got up to 56, which is still low, but it's not as low as it was, right? Green was the first rectangles we had. And then blue was the next lower estimate, right? So when I put in a new rectangle on the green, that allowed me to pick a higher point somewhere else in one of those 2 rectangles. The low one will still be in one of those 2 rectangles because the low over the entire interval was on one of these 2 rectangles, but the other one has a possibility of being higher. Okay. Here, the low for the blue was still 0, but the other rectangle, when I split it into 2, had a higher low, so that the underestimation with more rectangles was bigger after I added those more rectangles. Still an underestimation for the entire curve, but it's a bigger underestimation because I added more rectangles. Conversely, 160 was way overestimating, right? The orange rectangles were way overestimating. And then when I added more rectangles, one of the halves of that split stayed way up high, but the other one had a lower height than the entire thing. So I've taken away some of that overestimation, right? That stuff went away as part of the overestimation. That stuff went away as part of the overestimation. So with 4 rectangles, 120 is still an overestimation, but it's not as bad of an overestimation as when I only had 2 rectangles. The more rectangles gave me a smaller overestimation. Does that make sense? Kind of a weird trade-off. It's still over, but it's less. So you get a sort of a duality type thing there where you get more, but more causes it to not be as bad. So it was way over before, but it's not as over now after I added more rectangles. Questions on any of that stuff? Okay, let's do this one because this is another way we can do stuff. Okay, so let's read the question first. Using rectangles whose height is given by the value of the function at the midpoint of the rectangle's base, estimate the area of the graph using the first 2 and then first 2 and then 4 rectangles for x cubed between 0 and 2. Okay, so this is a midpoint estimation. Let me draw x cubed in here. So x cubed goes down and to the left and up and to the right. We're going to go from 0 to 2. First using 2 rectangles and then using 4 rectangles. Let me draw my verticals for my rectangles in. So if I'm using 2 rectangles, delta x is equal to 1. And this says to use the height at the midpoint of the rectangle's base. So here, the midpoint is at 1/2 and at 3/2. And so this is going to have two rectangles. They still have a width the entire thing here, so they'll still have width 1. But I'm going to use height f of 1/2 and height f of 3/2 as the heights, right? This is where I pick the height. Okay, so this overestimates on the right-hand side and underestimates on the left-hand side of the rectangle that I drew. And this rectangle that I drew overestimates over here, underestimates over here. And so this might be a better approximation if I have a function which is monotonic. So let's evaluate that. So this is 1 times 1/2 cubed is 1/8, plus 3/2 cubed is 27/8. So that's 28 over 8, which would be 7 over 2, or 3.5. Simplified fractions, 7/2. Okay. And now we're going to do it using 4 rectangles. Let's draw the picture again. Okay. There's 2, there's 1, 3/2, 1/2. There's going to be my 4 rectangles. My midpoints now are at the quarters. 1/4, 3/4, 5/4, and 7/4. And so the area using the midpoints as the heights of my rectangles. Again, overestimation, underestimation, overestimation, underestimation, overestimation, underestimation, overestimation, underestimation. So this will probably be pretty decent because those overestimations and underestimations look about the same size on each of the rectangles. But my width for each of these rectangles is 1/2, right? Even though I'm evaluating a quarter, the width of the rectangle is 1/2. And then I'm going to take f of 1/4 plus f of 3/4, because that's where I'm evaluating the heights to be, plus f of 5/4 plus f of 7/4. And then adding these up, I get 1/2 times 1/4 is 1/64. 1/4 cubed is 1/64 plus 27 over 64 plus 125 over 64 plus 7 cubed is 343 over 64. So over 128, and I've got 1 plus 27 plus 125, and it's 153. 153 plus 347, or 343 is 496. That's divisible by 2. This is 248 over 64, just divisible by 2. 124 over 32, 62 over 31, over 16, 31 over 8, 31 over 8. Okay. So questions on using the midpoint to evaluate instead of the left or the right? Okay, that's it for, no, today's Tuesday, isn't it? We have more time. Okay, good. Any questions over the midpoint stuff? Okay. Again, a midpoint estimate. This is just a review question, use implicit differentiation. Okay, so here I have a table, and it's a table of velocities. And this is just like the very first problem we did, only we have table values that we're going to estimate instead of the graph. Okay. So we want to estimate the distance traveled using 10 subintervals of length 1 second each with left endpoint values. So at time 0, I'm traveling 0. So if I kind of would have plotted this thing out in a graph, this table has values at 0, 1, 3, 4, 5, 6, 7, 9, 10. Right. And it says at 0, it's at 0. So I'm going to draw a dot there. At 1, it's at 5. At 2, it's at 11. 5 is probably too high if I put it there. Okay. So at 1, it's at 5. At 2, it's at 11. At 3, it's at 15. At 4, it's at 24. At 5, it's at 36. At 6, it's at 22. At 7, it's going 15. At 8, it's only going 8. At 9, it's going 5. And then it stops at 10 again. So I've kind of got this acceleration up and then deceleration back to 0. But if I'm going to draw rectangles in here and I want to use left-hand endpoints, well, in rectangles, I'm just going to draw these guys here, right? With left-hand endpoints. As being the heights. Does that make sense? And so all I'm getting is my left-hand endpoints. I'm going to take the delta x, f of 0 plus f of 1 plus dot, 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 plus f of 9 would be my last left-hand endpoint for the 10 rectangles. For the right hand, it would be the delta x. F of 1 would be the first right hand plus f of 2 dot, 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 plus f of 10. This would be the right hand. And so we can estimate this stuff with left-hand rectangles or right-hand rectangles, even though I don't actually know what's going on between the two estimates, between the 1 second estimates, right? I don't know what this graph does. Maybe it's really weird and it's spiky like this, and this is a terrible way to estimate these things. But we're assuming that we've got kind of a nice curve here, which maybe maxes out there and slows down here, right? As long as we kind of make some assumptions about how smooth this thing is, these endpoint estimates are going to be pretty good estimates for the area. This is an optimization problem, another review problem, another table problem like we just did. We got a speedometer, but no odometer. We want to know how far we went. As long as we're taking 10-second intervals, we could figure out how many feet we've traveled here by the velocity estimates. We're moving 40 feet per second for 10 seconds, so that's about 400 feet there, plus another 41 feet for the next 10 seconds, so another 400 feet, and then about 480 feet, and then about 220 feet, and so on. So I can add up how many feet I've gone using left-hand endpoints or right-hand endpoints, and so on. Now we're using 4 intervals. That's 4 rectangles, 4 subintervals of equal length, so equal width rectangles. And we're going to evaluate at the midpoints here. So this is a midpoint rule for x squared from 1 to 3 using 4 rectangles. Finite sums, 4 rectangles, equal length, midpoints again. So midpoint formula, 4 equal rectangle widths on the interval from 1 to 9. And then here we've got a leaky tank, and we want an upper estimate for the amount. So we're going to find the rectangles. And we only have function values at the interval, so the best of the integer. So the best we can do is have the sides of our rectangles at each of the integers. Because if I put the sides of the rectangles someplace else between the integers, I wouldn't know how big the function is between those 2 integers. Okay, so I'm gonna have my 8 rectangles here because I've got 8 integers from 0 to 8. And my width is going to be 1 each, and then I use the upper estimate. So on the rectangle, if it's between 0 and 1, I'm going to use the bigger number, so 55. Between 1 and 2, I'm going to use the bigger number, which is 150. So it looks like each one of these, the right-hand side is the bigger number, so this is a right-hand estimate for this one, for the upper. For the lower, it'd be the left one. Does that make sense? You cannot do a midpoint one because we don't know what happens at 1/2 or at 1.5. Okay, where do we have questions on any of this stuff? Okay, I'm going to talk just a little bit about some summation notation in section 5.2 for maybe not even 10 minutes, but I want to write that because it's super important and makes this writing these things down much easier. Instead of writing down like this expression when you have a whole bunch of things, I don't have to use the ... dots, which is nice. So summation notation. So if we're adding up a bunch of things that are similar, say with similar expressions, for example, I want to add, delta xi times f of xi, right? This is the width of the ith rectangle, and maybe I'm looking at just the left-hand endpoints or something, maybe the right-hand endpoints. So this would be the height of the xi rectangle. So if I want to add that up, add this for each I from I equals 0 to 10 or something, right? Well, we've got this sigma notation, which is a capital sigma. You put the expression in here that is dependent on an index variable. And then the index runs from wherever you tell it to run. Maybe you want to run it from 0 to 10. Okay, so this says for I equals 0 to 10, add up delta x sub I times f of x sub I. So I'm going to set I equal to 0. This is equal to delta x 0 times f of x 0 plus, well, from I equals 0 to 10, these are just integers on my index. The next one would be delta x1, f of x1. The next one would be delta x2. The last one would be delta x10. So the sigma notation, you've got some expression in here which depends on an index, and that index runs along some integers usually. 0 to 10 here would be those integers that that index runs along. Okay. You might see this in sequences and series. Say like AI equals 2 times 1/2 to the I, right? This is a sequence. Say A0 is 2, A1 is 1, A2 is 1/2. Every time the exponent on the 1/2 gets bigger, so I multiply by 1/2 each time. A3 equals 1/4, A4 equals 1/8. And so if I wanted to add up 2 plus 1 plus 1/2 plus 1/4 plus 1/8 plus 1/16 plus dot 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 forever, what I could say is add up from I equals 0 to infinity a sub I. Or we could write in the expression. We could write in add up I equals 0 to infinity 2 times 1/2 to the I. And that would say add up all of this stuff, but it's a lot easier notation wise to write down this than to decide, well, I think you can see the pattern after 6 of these things. Maybe you could have seen the pattern after 3 of them, so maybe I could have put the dot dot dots there. But then somebody didn't see the pattern after 3 of them, so I should have put the dot dot dots there. There's no ambiguity about what the pattern is here because it's explicitly written out. The pattern is take 2 and then multiply it by 1/2 I times, and that's what you do for the next thing in the sequence that you're adding up. Okay, so that's just a real brief bit on sigma notation, but we're going to use sigma notation quite a bit for these things. Like if I wanted to add up the summation from I equals 1 to 7 of I itself, this would just be 1 plus 2 plus 3 plus 4 plus 5 plus 6 plus 7, right? And so on. So that's sigma notation, and a lot of times it incorporates subscripts on things, especially when we're talking about sums of rectangles, which are called Riemann sums. When you're dealing with sums of rectangles under a curve to find the area of a curve, you're doing Riemann sums. And so we'll talk about sigma notation so that for 5.2, it's not completely introduced in 5.2 when we're trying to also introduce sigma Riemann sums. Okay, maybe some of you have seen that sigma notation before, but it's really useful. Okay. Any questions on anything from today before I let you go? Okay, I'll see you tomorrow.